Okay, so we're going to have a look today at our introduction to acid-base chemistry. The first two things we're looking at today, though, are going to be the Bronsted-Lowry definition of acid-base behavior and explaining this using equations, and also how we calculate the pH of a substance from its concentration, and also how calculating the concentration of an acid from its pH. So we're going to be looking at what's called the Bronsted-Lowry definition. There are other definitions. We're looking at the Bronsted-Lowry one because that largely is involved in aqueous chemistry. Before we do that, though, we need to have an understanding about what we mean by a proton, because we will often see a H plus ion, which we can talk about as being a hydrogen ion, interchangeably called a proton. They are, in fact, the same thing. If we think about a hydrogen atom has a nucleus which simply has a single proton in it and no neutron. And obviously it has an electron orbiting it. If we ionize this, so if we remove the electron to form an ion, we are left simply with its nucleus, with its single proton in it, and an electron. So we can use these words proton to define a hydrogen ion, or we could just use the hydrogen ion, but colloquially and in discussion we will often use the word proton. And in fact, when we're talking about the Bronsted-Lowry definition, we're often looking at a proton being defined there. So let's have a look at a straightforward example. So HCl gas, if HCl gas is dissolved in water, then we produce H3O plus, which is called a hydroxonium ion. So this is hydrochloric acid reacting with water, and it also produces a chloride ion. So this is at first good way to have a look at how we can define acid bases. So the hydrochloric acid has lost or donated the proton, so the H plus ion. So if we have a look at it, it was HCl, now it's Cl minus, so it must have lost a H plus. The reason we've gone from to Cl minus is we can think of HCl as effectively being a H plus ion and a Cl minus ion, although in reality it's more likely to be a covalently bonded compound, but that's how the electrons will break up and how we end up with the charges on these ions. If we have a look at what's happened to the water was H2O, it's now H3O plus, so this has accepted a proton. And this is where we get to our two definitions of what an acid is and a base is. So in this reaction, acid is a proton donor. So the substance that has acted as the acid here is HCl. We know that because it has lost a H plus ion and has just gone to be Cl minus, and the base is a proton acceptor. We know that because we've gone from H2O to H3O plus. And interestingly, water can act as both an acid and a base. Now I'm just going to write this equation out again to show you that we actually tend to ignore the presence of water in most of our equations when we're doing acid-base chemistry, because our water concentration is so high compared to anything else. All of these reactions are taking place in aqueous solution, that the effective concentration of water is infinite. Therefore, we can ignore it in our equations. So it's quite straightforward here. We simply write the reactants here as simply being HCl. But if we remove the water from here, what we're left with is just H plus. And what we've got here now is an equation that shows the dissociation of hydrochloric acid, HCl, in water. And it's very important that it takes place in water. Hydrochloric acid, hydrogen chloride, is not acidic until it has dissociated in water. So that's really important, and we'll come to look at this later because we can think about strong and weak dissociations. Let's look at another example. So NH3 is the formula for ammonia. Ammonia will also react with water, and it will produce an NH4 plus ion, which is called the ammonium ion. And if we have a look at what's happened to this, we've gone from NH3 to NH4+. So like earlier when we went from H2O to H3O+, what's happened here is we have accepted a H plus ion. If we've accepted a H plus ion, then we must be thinking about ammonia acting as a base. And the other thing that's produced is an OH minus ion or a hydroxide ion. What's happened to the water is it has lost a H plus ion. So this has donated or lost a proton, a H plus ion, and therefore it's acting as an acid. Okay, so taking these ideas forward, let's have a look at another couple of examples. So this is the formula for ethanoic acid. And H2SO4 is the formula for sulfuric acid. Now, this is one of the very earliest superacids ever created. Because sulfuric acid is such a strong acid, and we'll think about what those words mean later, that sulfuric acid is actually able to donate one of its protons to ethanoic acid. So we end up actually with this protonated form of ethanoic acid. And when the sulfuric acid loses a proton, it becomes HSO4-. Notice that any substance that is gaining the proton gains the positive charge. Any substance that is losing the proton now has a negative charge. So thinking about, and this is called the hydrogen sulfate ion. So what's happened here is ethanoic acid has gained a proton. If it's gained a proton, it's acting as a base, quite unusually because it's ethanoic acid. It's called acid, but when it's reacted with concentrated sulfuric acid, it will actually act as a base. And then sulfuric acid must have acted as the acid because it has donated a proton. Let's have a look at one last example. And our last example is the reaction between sodium hydroxide and ethanoic acid. Now this one's a little bit harder to understand because we've got the added presence of the sodium ion, which is going to potentially confuse us slightly, but I'll show us how we can shortcut that later. That makes this substance, which is called sodium ethanoate, which is the sodium salt of ethanoic acid, and it also produces H2O. So it's actually a little bit easier to understand what's happened to this one. So this was CH3COOH, and it has lost that H. So if it's acting as the proton donor, so it's donated a proton, donated a H+, it must be acting as the acid. If we ignore the Na for now, then we can see that what's actually happened here is the OH- ion has accepted a H+, and therefore it must be acting as the base. So what we can think about in terms of this, in terms of the sodium, is the sodium is actually a very, very stable ion, and in water it will actually just form an Na+ ion. So we can largely ignore the presence of the Na+. So in fact, our equation becomes a little bit easier to understand. Without the impact of the Na+ ion. Okay, right, so let's have a look at how we calculate some pHs. So the pH of a substance, mathematically, is the negative log of the hydrogen ion or proton concentration. So notice that I put H+ in square brackets. Whenever we see square brackets in chemistry, in this context, it means the concentration of H+ ions. So let's have a look at the pH of a solution of 0.500 mole per cubic decimeter nitric acid. So this is the last acid that we haven't seen in a common inorganic acid we haven't seen yet, which is nitric acid. So nitric acid fully dissociates in water, so completely dissociates, to give one H+ ion and one nitrate ion. That means if we have a concentration of 0.500 molar nitric acid, that must dissociate to give us 0.500 mole per cubic decimeter of H plus ions. Notice I'm just using a capital M here to as a shortcut to writing mole per cubic decimeter, and I'll do that from now on. So if we want to find the pH of this, we know that the hydrogen ion concentration is equal to the concentration of the acid. So the concentration of the acid was 0.500 molar. Therefore, when it dissociates, every single one of these molecules dissociates to give a H plus ion and an NO3 minus ion. Therefore, the concentration of H plus ions in solution is the same as the concentration of the acid, 0.500. So if we were going to work out the negative log of that, and that would give us a pH of 0.30. Notice that we tend to try and give pHs to two significant figures. Let's have a look now at the pH of sulfuric acid. So sulfuric acid is slightly different. So we're going to be looking at 0.200 molar sulfuric acid, H2SO4. So notice that there's actually two hydrogen potential protons that are donatable here. So H2SO4 produces two H plus ions and a sulfate ion. Strictly speaking, it doesn't produce exactly two, but for now we're simplifying it. And when we look at weak acids and bases, later on we'll be able to understand why this isn't, strictly speaking, fully true, but it's good enough for us now. So if we have 0.200 mole per cubic decimeter molar H2SO4, then that's actually going to produce 0.400 molar sulfuric of H plus ions. So we know that pH is equal to the negative log of the hydrogen ion concentration. We've inferred the hydrogen ion concentration by this relationship here. So it should be negative log of 0.400 gives us a pH of 0.397, which to two significant figures will be 0.40. The last thing we need to be able to do is actually do this process in reverse. So if we have a pH of a substance, so if we have, we're going to work out the concentration of HCl that has a pH of 1.70. So if pH is the negative log of the hydrogen ion concentration, then the inverse function of that, the hydrogen ion concentration, is 10 to the minus pH. So all we need to do here is go that the hydrogen ion concentration is equal to 10 to the minus 1.70, and that gives us a hydrogen ion concentration of 0.200 moles per cubic decimeter. And then we would say from that because HCl dissociates to give one H plus and one Cl minus, that if this has a concentration of 0.200, then this must have a concentration of 0.200. Thank you very much.